All right, so moving on to part two of the lab. This involves the chi-squared goodness of fit test. It's a statistical test. The letter X is basically the Greek letter chi, goodness of fit test. So when scientists do tests and they obtain numerical results, the results are often not exactly what they had expected. So this test determines whether the variations in the results are due to random chance, whether it's within the realm of possibility, or if there's something else going on that they haven't accounted for. To see how closely or good the observed actual results compare to the expected results, which are the ideal results. So for an example, when you flip a coin, what do you expect is the chance of getting a head versus a tail? Well, the chance is 1 in 2, which is 50-50. That's what you expect. But if you actually flip a coin 100 times, are you going to get 50 heads and 50 tails? Well, probably not. That's an ideal situation. So, I flipped a coin 100 times. I got 43 heads and I got 57 tails. I am lying. I did not actually do that. I got those values from the handout. I don't have the patience to flip a coin 100 times. Moving on. The question is what I actually observed, the difference between what I expected and what I observed, is that difference due to random chance? Is it just a normal variation, or is it something else? Is there something else meddling with the results? Is the coin weighted, or something? So for every chi-squared test, the null hypothesis, a null hypothesis assumes that the independent variable has no effect on the dependent variable. There's no change, there's no deviation. Similarly, in the chi-squared test, the null hypothesis is always that there is no statistically significant difference between the observed results and the expected results. A statistically significant difference is a difference that has statistical significance, meaning it is supported by the statistics. The alternative hypothesis is that there is a statistically significant difference, supported by statistics, between the observed results and the expected results. These are my results: 43 heads and 57 tails. That's the observed. And the expected is 50 heads and 50 tails. So I want to know, is this coin weighted? Or is this, within the normal realm of possibility? So to actually do this test, there's 3 steps. First, you find the chi-squared value. Then you're going to compare it to some standard values, which is on the table on page 4. And then we're going to decide which hypothesis is supported by the data. Mainly, we're focusing on the null hypothesis. Is it accepted/supported, or is it rejected/not supported? Please excuse my bad hair. So here is our formula. Chi-squared equals the sum of, this Greek letter sigma indicates the sum of the observed values minus the expected values squared over the expected values. Observed is usually represented by an O, and expected is usually represented by an E. So more often you're going to see this written as chi-squared equals sigma O minus E squared over E. And this value right here, this value right here is representing the deviation of the observed results from the expected results. So for my results, let's make a little table. The number of heads, the observed, what we actually got was 43 heads. What we expected was 50, because we want 50 heads and 50 tails. That's, normal. Let's calculate the chi-squared value for that, which is the observed, which is 43, minus the expected, which is 50. You square that over the expected, which is going to be 50. And if you do that math, it comes out to 0.98. And now we're going to do it for the number of tails. What I actually got is 57 tails, And what I expected was 50 tails, because you expect 50-50, a 1 in 2 chance of getting a head or a tail. So let's do the chi-squared equation for that. It's going to be the observed, which is 57, minus the expected, which is 50, squared over the expected, which is 50. You do that math, and you get 0.98. So now we still have the sum. We're going to add this value for the heads and the tails. Come on, autofocus, you got this. Which is going to be 0.98 plus 0.98. We're doing the sum of everything. And if you do that, you will get the value 1.96. This is our chi-squared value right there. So now we take it over to this delicious little table over here. We're on page 4 of the lab handout. Table 3, values of chi-squared. These are basically our critical values. Over here on the left, the first column we have DF, which is degrees of freedom. And that is the number of classes of results minus 1. In this case, we have 2 classes of results. We have heads and we have tails. So 2 minus 1 equals 1. Now we know we're going to be looking in this row for the answers. The next value we're going to look at is P. Now P is the probability. It stands the probability that our result, the deviation in our results, are due to chance alone. Usually scientists use P of 0.05 as a threshold. This means that you can be 95% sure you're either accepting or rejecting your null hypothesis. So if the null hypothesis is rejected or not supported, then that means the alternative hypothesis is supported. And if you do not support the null hypothesis, that means you're accepting, excuse my whiteout, you're accepting the null hypothesis. So if our chi-squared value falls in this column or above, then we know that the difference between our observed and expected is considered statistically significant, and the alternative hypothesis is supported, which means, remember, there is a statistically significant difference between what we saw and what we expected. There's something else at work. Now, if our chi-squared value falls to the left, then we know that the alternative hypothesis is not supported, the null hypothesis is accepted, which means that there is not a significant value or a significant difference between the observed and the expected. So we're looking in this column right here. Our chi-squared value, remember, is 1.96, and that's going to fall between 0.2 and 0.1 P probability. So let's say it's 0.15. That's pretty accurate enough. So that means it's below 0.05. The difference is not statistically significant. So we're going back to our hypotheses over here. There we go. Which means that the null hypothesis is supported by the data and the alternative hypothesis is rejected by the data. There is no statistically significant difference between the observed results, which is 43 heads and 57 tails, and the expected results, which is 50 heads and 50 tails. There we go. The coin's okay. It's not weighted. There's not another factor at work here. If we flipped it again and I got something more like 25 heads and 75 tails, we would do the chi-squared test again, and likely we would reject the null hypothesis and say that there is something wrong with the coin. That's all about the chi-squared test. Go ahead and answer the questions on page 4. Open up the quiz for part 2 and answer the questions. Bye! Oh, one more thing. Look how cute my cat is right now. Loki! Loki! He looks like such an angel. He's a god of mischief.